Okay, we have now gotten through the idea of what a critical point is and how to perform the candidates test. So we should get a little bit more information on the other type of our maximums and minimums. If you're just joining us, we're in the middle of topic 4, our applications of derivatives. The first part of this topic is all about what makes graphs or functions tick. So we're just trying to figure out what is the largest value on a function, what is the smallest value, at least on a closed interval, and we determined that last class. We've also, though, discussed relative minimums and relative maximums. For example, although this may be the maximum value of the opener, this is a relative maximum down here. And we're maybe not quite sure yet how we decide if a point is a relative max or relative min. Instead, we only talked about last class how to identify where the absolute max is and then the absolute min, or in this case, mins or minima. Today we're going to move one step closer to being able to identify where relative maxes and relative mins occur, but we're actually, even by the end of today, not going to be able to determine exactly where those occur. We're going to kind of build it up. Day 40 is going to be that big reveal of actually determining where a relative max or relative min is. So, nice little opener here. This takes you back to maybe Algebra 2. You're given the graph of f of x. It's in a very soothing blue on my screen, and your goal is to identify the approximate interval where f of x is increasing, where f of x is decreasing, and then where f of x is neither increasing nor decreasing. So not only should you try to figure it out on your graph over here, but you really want to try to figure out how you can write that as a sentence or as an interval on the right. So go ahead, take a quick second. Once you're done, unpause this and we'll chat. All right. Well, increasing and decreasing is really just a fancy way to say where is the slope positive, where is the slope negative, or maybe more accurately, where are the derivatives positive and the derivatives negative. So if we start at this first spot right here, the graph is going down. That is our negative slope. So we always talk, when we're creating an interval, we always talk about the x's, and it looks like we have a negative slope from -2 all the way over to 1. And then we have a completely flat slope, a slope of 0, so neither increasing nor decreasing from 1 to 3. Okay, and then we have an increasing slope from 3 to 5, don't we? So that's 3 to 5, and I should say increasing function, not increasing slope. That means something slightly different. And then we decrease from 5 to 7, so decrease from 5 to 7, and then we finish off by increasing from 7 to 8. Now, you'll notice that I didn't actually put brackets or parentheses around any of those because I was curious what you guys think. For example, do you think they should be open intervals, or rather, should they be closed? Does a function decrease until it gets to the endpoint and then start for the next interval, or does it increase through the endpoint and then overlap? For example, if I did put closed brackets on all of these, let's maybe take a look at this first part, and I'll zoom in on it. Right, we are decreasing, 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 and then do we stop here and then we do nothing here? Or maybe it would even be easier to see for this next part. Do I increase here, stop at the relative max, and then decrease on the other side? Or do I increase through this relative max, and then when I decrease, do I start at the relative max and decrease to the relative min? So do I use this point twice or once? And we are actually going to answer that right now. So let's go ahead and fill in a couple blanks. A function with a positive rate of change, that is a positive derivative, right, along an interval is said to be increasing on that interval. Positive rate of change, positive slope, positive derivative, if you'd like. A decreasing function, of course, has a negative rate of change, negative derivative, negative slope. Now, technically, we should only be discussing functions increasing or decreasing on an interval. Because a function technically increases or decreases relative to the points which came before. Now, what does that mean? Well, we really have to think of this line, and I'm just going to use this little line segment right here. We really have to think of this line as an infinite number of points. And as we go through and compare, let's take this first starting point and then the very next one, assuming it's infinitely close. And we have to ask ourselves, is this second point higher than the first point? And certainly it is, because we had to move up on the graph here. So we would say that this function increased from the first point to the second point. Okay, well, let's keep asking. That was an increase. Is this point an increase? Of course, because the point before it was lower. Is this an increase? Yeah, it's higher. Is this an increase? Cool. And then we get to the very last. Let's call this the second to last point here. Then we say, well, did we increase from this point to the point at the top? We certainly did. And so there's a pretty good argument that says when we talk about increasing, decreasing, we should have an inclusive or a closed interval here, where we start at the first point of the interval, we increase to the next, and we increase to the very last point. However, there is an equally valid argument that suggests that we should not do that, and instead this should be open, and we can only increase between the endpoints, so the actual endpoints aren't actually increasing to the next point. And so the AP exam has decided to agree with pretty much nobody who has an actual viewpoint and said, we don't care. So for increasing, decreasing, if you put parentheses instead of brackets, that's totally fine. No one's going to mark you off. And also sometimes people go a little bit far and they're like, wait, should this be an or between, or should this be should this be an and between, right? Our union versus our intersection. And the AP exam also doesn't care. And so honestly, I don't bother with that at all. I just write the word and, or you can even put a comma. You can say it's increasing on those intervals. It doesn't matter, but don't make your life hard by putting extra symbols in there. You should be fine. So, I also mentioned that we really shouldn't talk about if a function's increasing or decreasing at a specific point, even though it's a fairly easy one to discuss, because if I said right at this point, is the function increasing or decreasing? You're like, oh look, positive slope tangent line, the derivative here is positive, clearly the function is increasing, it's on part of a positive slope. But if increasing is defined as going from one point to a higher point, then increasing always really needs to compare multiple points. Of course, the AP exam doesn't care about that at all either, and it says we're just going to look at what happens at a single point, because between 2 points, we can find that slope that's a positive average rate of change. We talk about that even in Algebra 1. Calculus is all about the study of the rate of change of a single point. And so what we're going to be focusing on here isn't going to be that whole interval, but rather what happens at a single point. But luckily, again, we know calculus, and so all we need to do is look at the derivative at a point, and that should tell us the slope, or if the function is increasing or decreasing at that point. So we have our definition. This comes from your book, but it's not too terrible to think about. So given a function f of x which is differentiable, and don't forget we discussed 2 classes ago, if something is differentiable, it implies the function is also continuous. So again, this means we're not picking up our pencil and there's no sharp points, cusps, anything like that. So given a function f of x which is differentiable for all values c on some interval, then we say that the function is increasing at a point x equals c if f prime of c, so the derivative evaluated at that point, is greater than 0. And that should make sense because the derivative measures the slope of a function at a specific point, and if your slope is a positive number, that means your function has a positive slope and therefore increasing. Of course, the opposite is true. If f prime of c is less than 0, then we say the function is decreasing at x equals c. Now, before we actually do calculus, we have maybe 3 problems to work through today. Let's make sure we can understand what graphs look like if we're given some important information about the derivative, and make sure we can organize that information too. And we kind of did this last class, where last class we discussed what it looked like if the slope was 0 at certain points. But we didn't discuss these various intervals. And so what I'm actually fond of doing is making a sine chart first that's going to help us organize all of this information. Now, how do we organize this? Well, they gave us, I think, the key points on here. So what our sine chart is going to do is it's going to organize this information in kind of like a fancy number line. And so let's start with the important part of the number line, which is going to be the top of my sine chart here. Think of this, again, as a number line. Now, what important values go on here? Well, it's the important values they give you in the problem. They give you a whole bunch of intervals, and these are always x values on our interval, so we probably need all of these values. of course, hopefully you're saying, Mr. Grant, you said infinity is not a value. You're right, and this is also not actually a number line, so don't sue me. We are going to start at negative infinity, and the spacing here is very unimportant. Just make sure there's enough space between each number that we can fit some things in. We have 0, we have 4, we have 6, and we have, at the very end, I probably don't even need that last little point, I have infinity. There's my number line. But we actually want to understand what's happening on this number line, so I always turn this into a box. Okay? And in particular, I'm going to go ahead and close off the box at each of these points, but we're going to do a little bit more than that, because the interior of the box is going to tell us about the signs, hence Sine Chart. It's going to tell us about the signs of f prime of x. We don't need to know about the signs of f of x. That's really unimportant for us. We're much more concerned about the signs of the derivative. This is all about the derivative. So let's think about what's going on here. At our first value, at 0, right, it tells us that, actually, let's see, it says f prime of 0 is undefined. So I actually like to go through here, and you can turn your paper sideways, whatever works best for you, and I put a little DNE just to keep track. So I know the derivative is undefined there. Cool. What else do we know? Well, we know that the slope at 4 is equal to the slope at 6, and they're both equal to 0. So I'm going to go through and just show that these are slopes of 0 here, right? F prime of x does not exist. F prime of x is 0. Easy enough. Well, what else do we do? Well, they also told us about what's happening in between the endpoints. In particular, they told us that f prime of x is greater than 0 on these 3 intervals here, right? We have an interval here. I'm going to erase this here and here. So they told us about those 3 intervals. And we actually have space to do something about those intervals. So if f prime of x is greater than 0, that to me means f prime of x is positive on all 3. So I'm going to go ahead and put a positive on all 3 there. At the same time, they also tell us that f prime of x is less than 0, negative from 0 to 4. Well, what do both of those mean about our actual graph? The thing that I'm going to draw in here in blue, and I'll draw in blue over on the right as well, is going to be a general shape of our graph. In particular, our graph is going to increase. And when I say our graph, I mean f of x. So I'm going to say that the blue line is f of x. Our graph f of x is going to increase up until here, and then it's going to decrease until 4, and then it's going to increase all the way up to infinity. So I'm not going to do that. That just looks weird. Instead, we're just going to increase a little bit of the way and then finish increasing the rest of the way. Now, if you're doing this with pencil, you're going to want to sketch this really lightly, and I'm going to do the same thing as well, because you're going to add some curvature in just a bit too. But let's go ahead and sketch this graph. So they're telling us until we get to an x value of 0, my function better be increasing. Now an x value of 0 creates lots of points, 0, 1, 0, 4, 0, negative 2, 0, negative 5. So as my graph is increasing, a lot of people say, well, wait, 0, does that mean I stop at 0, 0? And the answer is no, you can stop anywhere you'd like. So I'm going to be bold and stop at, I don't know, let's stop at 0, 3, just to give you an idea that those are x's. So I'm going to increase, and again, do this lightly if you're in pencil, I'm going to increase until I get to 0, 3. Cool. After that, though, I'm going to decrease until I hit 4, something. Well, 4, what? I'm not really sure in this case, especially I'm noticing that my graph doesn't go up far enough, so let's put a few more points on here. I'll adjust this by the time you guys work through it. 4, I don't know, let's go 4, 0. Why not? So we decrease until we hit 4, 0. And then it tells us we're going to increase from 4 out to infinity. So 4 to 6 first, so I'm going to increase from 4 to 6, and then we continue out to infinity. There's a general shape of my graph. Nice. However, the one thing I haven't done is take into account what happens at those different points right here. So let's go ahead and take a peek. From this part to this part, or rather at an x of 0, here is an x of 0, the slope is not supposed to exist. Well, actually, that's pretty good. My slope doesn't exist there. There's that sharp point. There's a corner, whatever we're calling it these days. The slope doesn't exist there, so that's pretty good. Over at 4, though, it tells us the slope is 0. And if the slope is 0, that's where we have to have a bit of curvature. And so this is where your pencil comes in. So I'm going to say that this is actually going to curve down like so. And again, it's a little bit, if you have a pencil, you can be pretty creative, and you can actually make it curve just by putting in enough little lines there. At 6, we also have to have a slope of 0, so that's kind of up here. It has to flatten out. So maybe I'll have it, I don't know, let's have it go like this. And then after 6, it's going to continue going up, right? It has to, so maybe I can make this look a little bit nicer. It's going to go up, flatten out, and then continue up from there. So we have these 3 key points, 1, 2, and 3. And you'll notice actually that I think those 3 points are, if that's where the slope is 0 or doesn't exist, wouldn't we call these critical points? Isn't that what we learned last class? We have a critical point, another critical point, and a third critical point. Yeah, that looks pretty darn good. All right, well, what are we actually doing for the day? Well, unfortunately, in actual problems, people aren't usually nice enough to just tell you all of this information. They're not going to say, create the graph of f of x where you know all of this, right? What they're really going to do is they're going to give you an equation where you don't know any of it, and you probably won't know how to graph that equation either. You're going to go through, you're going to find those pieces of information, and then sketch a graph. Okay? So we actually need one more piece of information, though, in order to figure out these intervals, because I think we know how to find critical points. We did that last class. But the question becomes, how do we find out if our function is increasing or decreasing on these other intervals over here? And it's actually not too crazy hard, because we already know where the intervals start. How do we know where the intervals start? Well, look at our graph over here. What is splitting up the integral, or the intervals? We have an interval that was split here, and over here. Oh, take a look at that. The intervals are split by critical points. So if we combine what we learned last class and we find the critical points, then that's going to help us split apart our interval. Once we've split apart our interval, actually figuring out what the derivative is on that interval is pretty straightforward, and I'll show you that in just a second. So by examining past graphs and using our intuition, we should be able to determine that a graph can only change slope at a critical point. So let's see how that helps us. Okay. List the intervals on which f of x equals 2x cubed plus 3x squared plus 1 is increasing and decreasing. Well, step 1 is easy. We're going to go ahead and take the derivative, because we're going to find those critical points so that we can separate out our sine chart. So, derivative first, f prime of x equals 6x squared plus 6x, plus 0. 1 goes to 0. That's awesome. Super cool. And I mentioned before, if we can, we're going to try and factor this. Pull out a 6x. This becomes x plus 1. 6x times, that x plus 1. Cool. We haven't found critical points yet. We need to look at where the derivative is both 0 or undefined, but this is a polynomial, never undefined. Phew, that makes life a little easier. We just need to set f prime of x equal to 0. We know the equation for f prime of x, that's 6x times x plus 1. Two equations, 6x equals 0 or x plus 1 equals 0. That's the zero product property. X equals 0 or x equals negative 1. Nice. I found critical points. How does that help us? Well, now we can make a sine chart. That's really, really useful, right? If I want to go through and make a sine chart here, I'm just going to set up my nice little rectangle. We go from negative infinity to infinity. And the reason we're doing that is because they didn't give us an interval, so we assume the whole x-axis. We are going from 0 and 1. Those are important. And we know that both of these values, if we put them into the derivative, will make the derivative equal 0. That's the whole point of setting it equal to 0. So we know that these make the slope, or the derivative, equal to 0. We have 3 intervals on this graph. Now let's record what we've done so far. There are a few steps to list the intervals where graphs are increasing or decreasing. First, we find the critical points, and that's what I did in red up there, by determining where f prime of x equals 0 or is undefined, DNE. Nice. Step 2, create a sine chart using the critical points as dividers for your intervals. Oh, we did that. That's very exciting. Now, to determine the sine of f prime of x, and I forgot I should probably label this as f prime of x, to determine what sine is in here, we need to be a little creative. And we're going to be creative by realizing what we did on this graph on the first page. In particular, and let's just use this first little line over here, what is the slope at any point on this first interval? And I'm not looking for a number. I'm hoping that you're going to say the slope is always positive. Okay, well, what is the slope for any value on this next interval? Always negative. Third interval, always positive. Fourth interval, always positive. By identifying the critical points, we have found the only places that the slope can possibly change. And notice it changed here, the slope changed here. It didn't change here, but that's okay, because we just wanted to know every place the slope could change. And that's important because jumping back down to our sine chart, we have identified the only places the slope can change. And so if the slope cannot change in here, then whatever value of f prime we get for any of these numbers on our number line, any other number here is going to have the exact same value. Not in terms of the actual numerical value, but in terms of if the value is positive or negative, right? Again, going back up here, let's say I was looking in this interval. Well, f prime, every single value here in f prime would give a negative answer because there are negative tangent lines. So jumping back to this, if I wanted to go through here and figure out what is the sine of f prime, or rather what type of slope do we have here, we're just going to pick a number from 0 to negative infinity. I choose -2. Sounds like fun. So if I choose this should be -1. I switched those. Sorry, guys. I decided 0, 1, and then I'm looking at it like this doesn't make sense. -1 goes before 0, and it should be a -1. Awkward. Okay, so I'm going to go ahead and choose a value that's between -1 and infinity, and I'll choose -2. Why not? Now, I usually don't write the -2 up above. You don't have to. So I'm going to find the value up here for f prime of -2. Well, f prime of -2, we have an f prime equation. It doesn't matter which one you use. I like using the factored form. I think life is a little bit easier that way, but it's up to you. 6 times -2 times -2 plus 1. This becomes 6 times -2, sorry, I should zoom in again, times -1. Well, I don't even care what this equals in terms of the value. I just care about if this is positive or negative. So negative times a negative, that's a positive, times another positive, that is certainly a positive. Now, of course, the math isn't hard. 6 times 2 is 12, an extra 1 is positive 12, but who cares about the 12? I just care about the positive. Because -2 gave me a positive answer to my derivative, that means any value here is going to give me a positive answer to my derivative. So I know that in here there is a positive derivative for every value, or a positive slope, or our function f of x is increasing on that interval. Let's look at the other two. We need to use a value between -1 and 0, and I imagine most of you would say, ooh, -1/2, that's between -1 and 0, and I totally agree. 6 times -1/2 times -1/2 plus 1. I'm going to do almost no simplifying here besides saying 1 minus a half is a positive half. And then think about the multiplication. A positive times a negative times another positive, that's a negative value. I think technically it's -6/4, but again, I don't care. It is negative. And what that tells me is any value between 0 and -1 will also be negative. Last but not least, let's look at this guy over here. We're going to try, oh, and I forgot my prime right here. I'm definitely plugging these into the derivative because the derivative tells us about the slope, and that's what we're trying to find here. We're trying to find increasing, decreasing. We're trying to find our slope. Last one, we're going from 0 to infinity. Let's just try 1. Why not? 6 times 1 times 1 plus 1. I'm pretty confident all of those are positive numbers. Okay, so we've created a sine chart. That is very exciting. In fact, if we wanted to fill this in, and I'll do my function f of x in purple up here, we can see that our function will increase, and then decrease, and then increase. All right, we don't know where it's curvy. Curvature is going to get covered later on. We don't know too much more about that, but we do know a general shape of our graph. And I bet it doesn't surprise you. Like, it's a cubic graph. A cubic graph goes up and then it goes down, right? It adds curvature there. But either way, this gives us a really good indication of at least where our function is going up and going down, where f of x is increasing and decreasing. So let's see what we need to add here. Create a sine chart, blah, 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 to determine the sine of f prime of x in each interval. Evaluate an x value in f prime of x. That sounds awesome. Now, unfortunately, this is not enough to justify your answers, because almost every problem where they ask for increasing, decreasing will say, okay, cool, you found that, but can you justify? And actually found that. We didn't even explain the intervals where the function is increasing and decreasing. And I'll tell you right now, a sine chart is not an accepted justification on the AP exam. I always draw a sine chart, but you cannot use that as a conclusion. You can't say, because in my sine chart there is a positive here, then my function is increasing. It's got to be better than that. And the nice part about having a sine chart, though, is you just write what's in the sine chart for your conclusion. And so I'll probably do this off on the side. Sorry, I've run out of room, but that's okay. Here's what we do. Right? We would say f of x is increasing, very common, INC for increasing, right? Increasing on, we have two intervals here, parentheses for infinity, right? To -1 and from 0 to infinity. How do I know it's increasing there? And that's literally a question I'm asking you. I know the function is increasing there by looking at my sine chart, or in particular, realizing that f prime of x is positive in those two intervals. The reason I knew to draw my purple graph going upwards is because of those positive signs. So f of x is increasing on those intervals because f prime of x is positive. And you could literally write out the words f prime of x. So you could say f prime of x is positive. You could say f prime of x is positive and write it out, whatever sounds good to you. It's pretty common to use this greater than, though. So we're saying f of x is increasing on those intervals because f prime of x is positive. And that's it. So you don't have to show any extra work. You just need to state what is in your sine chart over here. And once you've stated those, you're set. That is the justification, and it's a very easy justification, right? There's no work to back it up. It's just, did you get the intervals, and did you explain why you knew what was happening on those intervals? Of course, we should do decreasing as well. It's just as easy. F of x is decreasing on -1 to 0, and again, you can use parentheses here or brackets, whatever makes your heart happy, is decreasing on that because f prime of x, what is f prime of x on that interval? F prime of x is negative, so f prime of x is less than 0, right? We're just referencing the function and the signs for that function. And that's all there is to it. So write a conclusion that uses the information in the sine chart, but without using the phrase sine chart. And that's it. It's a really easy way to organize your work and actually get everything that the AP exam requires. Now, let's make sure I actually got this right. It's very easy to check with your calculator. We just graph the original function up here, 2x cubed plus 3x squared plus 1. 2x cubed, 3x squared plus 1. Look, we increase until -1. We decrease until 0. And then we increase all the way on out. Cool. That's exactly our graph, except ours is straight. It doesn't have curvature because we're not going to add that till later on. Nice. Nothing to it, guys. So now that we at least have our role here, our steps, let's go ahead and see what we can do for this next one. Okay, same idea, but slightly different function. Now you could take the derivative of x times e to the -x, but I don't like that negative exponent. I think it throws people off a bunch. So what we might remember is that we can really write it as 1 over e to the x, right? Negative exponent. Or even we can combine this as x divided by e to the x. And strangely, this is one of those where I'd actually rather use the quotient rule than the product rule. It doesn't matter. In fact, the product rule might be faster. I was just thinking quotient rule, and I figured, let's practice it. We haven't done it in a while. So quotient rule. G prime of x, derivative of the top, keep the bottom the same, keep the top the same, and then derivative of the bottom. But the derivative of e to the x is just e to the x. Okay, good so far. And then we take the bottom and we square it. Cleaning this up slightly, and again, if you have the chance to simplify a derivative, when we're finding critical points, it's usually a good idea because you're going to have to solve this at some point, so we might as well make it look nicer. So I have e to the x minus x e to the x divided by an e to the x squared. Since I notice there's an e to the x on the top, I'm actually going to rewrite e to the x squared as e to the x times itself. You should know, though, that e to the x squared is actually e to the 2x. It's not e to the x squared, and that's because same base, you add the exponents, right? So I think maybe one or two more steps here. We can factor out an e to the x. That leaves me with 1 minus x divided by e to the x times itself, and these guys cancel. So it looks like g prime of x is 1 minus x over e to the x. Okay, next step, if we want to identify increasing, decreasing, we need to find our critical points. So critical points occur at two places. They occur where g prime of x equals 0. Now, instead of setting the whole fraction to 0, though you can, we need to remember that a fraction only becomes 0 when the numerator is 0. 0 divided by anything, so I'm really just going to set 1 minus x equal to 0, and we get x equals 1, first critical point. Easy. We also need to realize that g prime of x does not exist if the denominator becomes 0. But if you set e to the x equal to 0, I think you're going to have a tough time solving this. You should think exponents first. Is there any exponent you can think of that if you replace it with a number, the answer becomes 0? Because if you choose 0 up here, the answer is 1. If you choose 1, the answer is e. If you choose negatives, the answer is just a fraction. And so I think you'll find, or maybe remember, that there's no value that makes this equal to 0. However, if you wanted to go about it a different way, you could undo e to the x by introducing a natural log. And that gives us an x equals, oh wait, you can't do any log of 0, so we just get does not exist, which tells us that there's no value that makes our derivative undefined. Sweet! Sine chart. All right, we have g prime of x here. We need this guy. They didn't give us an interval, so we're going negative infinity to infinity. There's only one critical point this time. Rock on. That's 1, where the slope, where g prime is 0. And then we just need to test values in here. And again, I'm just going to use this part, and it shouldn't be too hard. If I try, I don't know, 0 in here, right? The denominator is always positive, actually. Why would I even plug anything into the denominator? That's always a positive. So we get 1 minus 0 over something that's always positive. I think that's going to give us a positive answer, 1 divided by a positive. If we try like 2, then we get 1 minus 2 over a positive. That's a negative divided by a positive. That's going to give us a negative here, except I wrote a positive, so that's awkward. There we go. And then visually, we can see that g of x, which I did in black, and notice I'm very careful to say g of x, that's what the problem asked for, is increasing from negative infinity to 1 and decreasing from 1 to infinity. And I'm careful to say g of x is increasing, not g prime is increasing. G prime is not increasing. G prime is positive. When g prime is positive, g is increasing. And they are incredibly picky. If you mess that up, you almost always lose a point. G increases when g prime is positive. When g prime is positive, g increases. However, quick conclusion, right? G is increasing on negative infinity to 1 because g prime of x, and I'll switch it up, is positive. You could say g prime of x is greater than 0, right? Nothing too bad. I just went a different route this time. We also know that g is decreasing on 1 to infinity because g prime of x is negative. Right, so hopefully you're understanding now at least a little bit more of how our derivatives fit together, and also understanding that you don't need to learn any new derivative rules. We know all the rules. Now we're just applying them. We're just going a step or two further. We're taking our derivatives, setting them equal to 0, which we did in the past, solving. We just have this last step of actually understanding what those derivatives are telling us. The last page of this is not bad at all. The last page asks you to try sketching these problems below. So your goal is to go through, using all of this, create a sketch of that graph. Now, what I'd like you to do, please, is actually create a sine chart first. So this one is going to have a sine chart for f prime of x, right? And this guy over here is also going to have a sine chart for f prime of x. After you make the sine chart, use that to help you sketch your graphs, and you should be good. Once you're done with those, then we will go through the last one together. If you want, you can work on ahead and, of course, check your work. All right, let's get this sine chart rocking and rolling. We know if f prime of -1 doesn't exist, that's a critical point. Nothing too bad, and again, writing sideways on my tablet is always a little bit weird, so bear with me there. It says DNE. We're going from -infinity to infinity, and we know that f prime is greater than 0 on the left side, less than 0 on the right side. So that tells me my function increases and then decreases. Okay. So there's a couple ways you could graph this. I mean, the easiest is realizing -1's our critical point. So you could just graph it like that. That meets all the requirements. Very exciting. However, you can be a little more creative and you can give your function some curvature. Maybe I'll make it come to a cusp. So I'll make it end up here, and then we can also have it curl back down this way. Right, there's that cusp that we see, and that's about it. I made it stop right around 2.5, but there is no y value given here, so you can pick any one you want, -1 comma something. Okay, let's look at one more. Couple critical points here. We have -2, and they tell us that slope is 0. 2, the slope is 0. 4, the slope is also 0. Infinity, -infinity. And what did they tell us at the end? F prime of x is greater than or equal to 0 the entire time. So positive, 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 positive. Nice. So I think all our graph is going to do is just start down low and increase like so. Except every time we hit a critical point, we have to have a slope of 0. Okay, I think we can just make this kind of curvy, wavy, and it's going to look something like this. So -2, I should probably circle these so I remember what they are. -2, 2, and 4. My graph is going to be going up, and then hit a slope of 0, and then be going up, hit a slope of 0, and then be going up, hit a slope of 0. Kind of reminds me of like a dinosaur or sea snake or something like that. And that's it. You can always plot the critical points if you want, something like this. Okay, but we can see that everywhere on this graph my slope is positive, or at these critical points, 0. Nifty. Last problem. You're going to want a calculator for this one, just for one part where we test the intervals. Having done this problem a couple times before, I like the solving. I think it reminds you of how to use natural log, but then when you have to plug values in, natural log of values are pretty gross. So let's begin. All right. Increasing, decreasing, we got this. First step, derivative. Oh, the derivative. Notice we have two functions multiplying. It's our favorite product rule. We did a quotient rule earlier. We might as well do the product rule. Derivative of x squared is 2x. Keep natural log of x squared the same. And then add on the original x squared. And then this one always throws people off. The derivative of natural log of x squared is 1 over what's inside. That's the natural log part. But what have we not done the derivative of yet? We haven't done the derivative of x squared. And the derivative of x squared is 2x. Can we clean this up? Oh, most certainly. This is 2x times the natural log of x squared. And then notice that there's all multiplication here. We can do the multiplication in any order, and I'm going to choose to do this multiplication first because they cancel each other out, and that just leaves me with an extra 2x at the end. We might now notice that there's a 2x in common to both terms, so I am going to factor that out as well. And I think we end up here. That's probably about as factored or simplified as we need. Let's find those critical points. Okay, 0 equals 2x times the natural log of x squared plus 1. Two equations. 2x equals 0, or, zooming in a bit, or the natural log of x squared plus 1 equals 0. The first one, divide by 2, we get x equals 0, nothing terrible. The second one, we need to go through, subtract 1 from both sides, and then I'm going to probably run out of a bit of room here, but that's fine. But that's okay. We're going to exponentiate each side. There's a caret there. So that gives us x squared equals, and we should have done different color, e to the negative first, And I am going to go ahead and, oh, there's a little bit of space up here, so we're going to use this cute little space, and this is terrible, so don't let your teacher see that we're showing work this way. That's okay. So we end up with really x squared, e to the negative first is just 1 over e. And then we need to take, of course, the square root of both sides. Don't forget that when you take the square root, you need to introduce a plus minus. And I think we can simplify this even a little bit further by distributing the square root to the top and bottom. Square root of 1 is 1, and it just becomes that guy. Okay? And if it helps you visualize where that is, remember that e, I should put approximately here, remember that e is that 2.718, so on and so forth. So think of this as like 1 over the square root of 3, 1 over the square root of 2, somewhere in there, right? It's a little bit smaller. Square root of 4 is 2, so it's a little bit smaller than 1/2. All right, sine chart time, finally. I've used so much red, we're going to switch it up. Here is my sine chart. It's a pretty good line. Oh, and then I had to say something and screw up the rest. So let's try again. There we go. And we have f prime of x. We're on, well, are we on negative infinity to infinity here? Because I think I forgot to check something. And you won't have to write anything, so no stress. I only found where the derivative is 0. And I forgot part of our critical points. In particular, I forgot to find critical points where f prime is undefined, because f prime is undefined in a great many places. And it's undefined due to this natural log. So we need to know a couple things. First, we need to know that the natural log of, or actually I said a great many places, it's really not, it's only 1. We need to remember that you can't take the natural log of 0. I really should probably redo this. So let's go ahead and let's do that part too. Let's be a good math teacher for once. We need to also determine where f prime of x does not exist. Okay, and this is always a little bit trickier on our function analysis, and usually the problems aren't this challenging, so don't stress it too much if you're a little lost. The only thing that's going to cause this function to not exist is this natural log piece. So we need to remember 2 things about natural logs, or any logs. First, natural log, right? We cannot take the natural log of 0. So we need to ask ourselves, when is natural log of x squared, what x value makes that 0? And hopefully you're saying, oh, well, that means that x can't be 0. If x can't be 0, then that is actually a critical point here, right? If we were talking about the domain, we'd say x can't be 0. But here we're actually saying x equals 0 makes this undefined. All right, cool. Well, the other thing that natural log can't be is natural log can't be negative numbers. But we're actually lucky here because we're squaring a value, and whenever you square a value, it becomes positive. So the natural log will always take positive numbers as its input, so I think there's only one critical point here that occurs when the derivative doesn't exist. And actually, I'm not super worried about that because I found that critical point over there anyways. Whew. Okay, I'm not that bad of a teacher. Here we go. F prime of x, sine chart time. Negative infinity to infinity, and beyond. And then we have, of course, 3 critical points. 0 causes, well, does it cause the slope to be undefined or does it cause it to be 0? I would actually argue this probably causes it to be undefined. My guess is, since you can't even use 0 in the original equation, there's just nothing there. So I'm going to put a D and E. Then we have 2 other critical points here. We have the critical point negative 1 over the square root of e, and that caused our slope to be 0, and that's supposed to be an e, not a 2, and then I just deleted the whole thing, so I'm really doing well here today. Second try, there we go. And we also have 1 divided by the square root of e, which causes the slope to become 0. Now I think you might understand what I mean about you're going to want an equation to evaluate these in. So let's go ahead and figure out what's happening with all of our slopes here. Okay, so in order to do that, we need to find 4 values on these intervals. Well, I know 1 over the square root of e, that's going to be probably smaller than e at this point. So we could use e here if we wanted. Eventually we're going to plug something into this equation, but I don't even think we need to worry about that. I mean, imagine if you just use like 10 here. If you put 10 into the derivative on this side, I think everything's going to be positive. There is no way we're going to get any negatives. That's positive there for sure. Okay, but the rest of these might be a little challenging. So you might want to go through and use your calculator to fill in these three. Okay, and I'm going to be a little bit lazy here. You should use your calculator, but I'm just going to quickly show us that graph. And I know I never showed you the graph of x times g, or x times e to the negative x, but we did get it correct, I promise. Right, there's one critical point that's right up here. Look at that guy, right? And then everything else looks fine. Let's look at this last graph, though. The last graph looks something like this. And notice, we are decreasing until here, okay? And then we increase until here. Undefined, I wasn't wrong. We decrease until here, and then we increase after. Notice this 0.607. What do you think 0.607 is? I bet you're already guessing. Oh, 0.607, that is our square root of, or 1 divided by the square root of e. So again, looking at this graph, we can see our table is going to be negative, then positive, then negative, then positive. And so jumping back over here, right, negative, positive, negative, positive, that tells us that our graph will decrease, then increase, then decrease, then increase. And there we have that rough shape. I mean, we saw the graph went something like this, and that really fits the shape that we have down here. Nice. Well, that's all there is to it. We probably should write a conclusion for this one, but I'm pretty much at the end of this, and I think you can do it okay, right? We would just say that f of x is increasing on these two intervals because f prime is positive, and then of course we'd say f of x is decreasing on these two intervals because f prime is negative. So thanks for sticking with me. Hopefully you're feeling a little comfortable for increasing, decreasing intervals. It was a pretty rough derivative to end with, but the rest of this hopefully was not too terrible.